All right, well, welcome back. So we'll pick up where we left off, but let me, since, it was a long time ago, let me just kind of briefly remind you what we're talking about. So, okay, so we're looking at functions. So this is called our activation function. In the situation that I'm talking about is the function max of 0 and x. And so we're looking at functions built by composing multiple layers where each one is an affine linear map followed by this nonlinearity. So just to get us warmed up, let me do an example. So this is going to be a very, very small little toy example. Let's say my architecture is 1, 2, 1. So that means I'm looking at maps that go from R1 to R2 to R1. So this one, the first layer map, is going to be an affine linear map followed by this. So an affine linear map from R1 to R2 is going to have the form x goes to, let's say, ax plus b in the first coordinate, and we do the nonlinearity, and cx plus d in the second coordinate. And then to go from R2 to R1, we need another affine linear map. So it will be some number of multiples of this one. So let's see, A, B, C, D, E. E times sigma of ax plus b plus, and then F times this one, F times sigma of cx plus d, and then I need a plus g, and then I put the sigma all around it. Let me draw a picture to go with this. So let's say we start with R1. I can think of, I'll draw this coordinate, sigma of ax plus b. So this is going to be sigma of ax plus b. Okay, so ax plus b is just, that gives me some line. Let's say it looks like this, for example. And now when I do the sigma, what sigma does is if it's a negative value, it turns it into a 0. And if it's positive, it's the identity. So the graph of sigma of ax plus b will make all these negative values 0, and then just keep all of these. And then let's see, maybe the other coordinate, let's say this is sigma of cx plus d. I don't know, let's say the line looks like that. And again, then the ReLU, the sigma, makes negative values 0. So actually our function looks like this. Okay, and then to go to R1, we got to add multiples of this and that. I'm going to make E and F positive in my sort of cartoon picture. Let's make everything positive. So I take some of these and I add some of these. So let's see, over on the left, it's going to be kind of sloping down until it gets to wherever this point is. And then it continues, this one's going down, but that one's going up. I don't know, maybe it does like that or something. And then you get to here, or no, you get to here. Now this part's contributing 0, this is contributing positive, so it goes up again. Okay, so, and so where are the nonlinear parts? So this happened at the point x equals negative b over a. And this happened at x equals negative c over d, which, because we're in one dimension, this is a hyperplane, right? Because a point has dimension 0. In one dimension, the difference is one dimension. So these 2 points are actually hyperplanes. So we can pull them back to our original domain. Maybe here's 0. So this one is like there. This one is like there. Yeah, okay. And so basically, we now have taken our original domain and we've cut it into 3 pieces divided by these hyperplanes. Okay, so that was the warm-up. Visualizing these things. Now we're going to go back to slightly higher dimensional case. Okay, so in this example, we were talking about a map from R2 to R3. Oh, and we were talking about the sign sequences. Let's do that here too. So we'll call this one neuron 1, and this one will be neuron 2. So in this region, neuron 1 is 0, neuron 2, or it's like this one is off, this one is on. It's like a negative and a plus. In this region, they're both on, so it's like a plus and a plus. And then in this region, this one is off, this one is on, so it's like a negative and a plus. And then if you want, you can code these points as being zeros. Like this is maybe this is like a 0 plus, and this one is like what is that? That's wait, did I do that right? Yeah, 0 plus. Wait, something's wrong. Plus minus? Okay. All right, so then this is like plus 0, this little point right here. So I'm attaching these signs to each cell in my simplex. Okay. Yeah, okay, so this was illustrating that again. And the point, just to emphasize it again, is that there are hyperplanes. So this point was a hyperplane because we're working in R1. In R2, a hyperplane is a line, and so on. Okay. All right, so let's just say this a little bit more formally. So here's our function. So each of these layer maps, F1, F2, gives you an arrangement, and by arrangement I just mean a collection of hyperplanes in the space that's the domain of that map. So like F2 gives you a bunch of hyperplanes in Rn1. F1 gives you some hyperplanes in Rn0, and so on. But what you can do is take these hyperplanes, say the hyperplanes in Rn1 that came from F2, and you can take their pre-images in Rn0. So you can like pull everything back all the way to the domain. So when you do this, you find that the total map, F, like the whole thing, it's linear except on these pre-images of the hyperplanes. And this is just writing it in, right, as like H is the hyperplane associated with the jth coordinate of the ith map. It's just pull everything back to the domain. So these pre-images in your domain are called bent hyperplanes, and their union is called the bent hyperplane arrangement. Connected components of the complement of the bent hyperplane arrangement are called activation regions. Okay. So sort of almost automatically, just because of the way we've kind of built this, we have that our map F is linear on each activation region. And we also, for each activation region, you can associate to it a sequence of signs. So for each neuron, each coordinate, you have a plus, a 0, or a minus. So in the example I did before, I recorded the sign sequence for just a single layer, but when you pull everything all the way back, you can record the sign sequence with respect to every single neuron. Okay, good. Okay, great. So what are these things that we're getting by pulling back all these hyperplanes, right? So you start with hyperplanes, and then you start drawing these ones that go like this, these bent hyperplanes, and right? So what we're doing is we're cutting up the domain into polyhedral sets. So part 2 is background or the background definitions associated to polyhedral sets. So a polyhedral set in Rn is the intersection of finitely many closed half spaces. Just a fancy way of saying, you know, it's something with flat sides. A polytope is a polyhedral set that is bounded. So, for example, this is a polyhedral set in R2. It's unbounded. It's not a polytope. Like, these are polytopes because they're bounded. So, some terminology. So, a subset of a polyhedral set, I'm going to use P for a polyhedral set, is called a face of that polyhedral set if either it's empty, it's the whole thing, or it's the intersection of your polyhedral set with some hyperplane that touches it, but only on its boundary. So, like, for example, let's say my polyhedral, oh, I actually did an example. Let's say my polyhedral set is just this filled-in triangle in R2. Let's list all of its faces. So there's the empty set, we got that. There's the whole thing, it's there. And then one way you could get a face is you could take, you know, the hyperplane that goes along there, and that gives you that edge. Then there's the hyperplane that goes along there, that gives you that edge. There's the one across the bottom. And then you could also make a hyperplane just touch at the vertex, and so you have 3 0 cells. So those are all the faces. Okay. So a polyhedral complex in Rn is a collection of polyhedral sets that satisfy 2 properties. The first property is that if P is in your collection, then all the faces of P are also in your collection. So I couldn't have, for example, a triangle but not have an edge of the triangle. Like, you have to have all the smaller pieces. The second one is that if you have 2 sets in your complex, the intersection of those two sets is a single mutual face of the 2 cells. So this example right here is not a polyhedral complex. And that's because it violates condition 2 here, right? So if I look at, say, the intersection of like P and R, the intersection is just this part right here. But that's not a face of P, because the face of P is this whole thing. So that's kind of the distinction. Like, when cells touch, they have to touch along a whole face. They can't touch along part of a face. Okay. A polytopal complex is a polyhedral complex where all the cells are polytopes, meaning bounded. And then the underlying set is just the union of all of the pieces. So for example, for that filled-in triangle, right, this is actually, it's actually a list of cells. There's this, there's this, there's this. It's like a list. That would be the complex. But this would just be like the actual union of all the points in all those pieces. Okay. So next, let's talk about piecewise linear maps between polyhedral complexes. Okay. So we've got a function f, and it goes from, well, in this case, Rn1 to Rn2. And let's say we've got a polyhedral complex M that lives in Rn1. We've got another polyhedral complex N that lives in Rn2. Okay, and we can assume that this function is continuous and also that it's piecewise linear or affine linear on each cell. With me? Okay, so if you've got this, then you can define something called the level set complex. So M is the complex in the domain. And I'm going to use this notation, F in N. What it means Oh, well, here's the definition. So you take a cell S that's in M, and then you take the pre-image of a cell that's in N, and it's the intersection of those two. Let me do an example. Okay, so here's an example. Let's say M. Let's say we're going to be on R, N1. Let's just say that's R1. And let's say N is also Rn1, or also R1. And let's say my function, f goes from R to R by, I'm just going to make up something. Oh, I need to give myself a polyhedral complex. M is going to be, I take my polyhedral complex, and it will have, this is 0, and let's say it has, this is a 1 cell, this is a 1 cell, like an unbounded 1 cell, and then there's a 0 cell. This is my N. And let's say my map F goes from M to N, and let's just say it's F of X equals AX plus B for some A and B. And let's say N, I'm changing my example as I'm going to make N just the single cell 0. Okay, so now let's think what this says. So in this case, N is just the single cell 0. So if I take the pre-image of that 0 cell, that's just a point. And then I take each of my 3 cells and I intersect it. So maybe this is the pre-image. So this cell intersect that is empty. 0 intersect that is empty. This intersect that is just this point. So the pre-image, the level set complex would be the single point consisting of this point. Okay. Lemma, this thing is a polyhedral complex. So those 2 properties that characterized a polyhedral complex were it contains all the faces, and then things intersect along full faces. So it's still true. Okay. So of particular interest, oops, that was supposed to be the word interest, is sublevel set complexes. So you have some map F that goes from one complex to another complex on R1, where N is, you pick a threshold, and it's either everything that's like below T and faces of this set. So N equals basically like, if here's my real line, it's like, and this is T, there's like this 1 cell, and then there's like a 0 cell. So the complex associated to this map is like you pull back N and you ask what part of your original complex do you get? So M, F less than or equal to T, it is by definition this level set complex. Basically, it's like everywhere where your map takes on a value below T. You can define a super level set complex the same way. Questions so far? Everyone's good? Okay. So part 3, I want to talk about genericity. So first, I have to tell you, I lied to you. Well, okay, I didn't quite lie to you, but it was a little bit misleading. So in our earlier discussion, we talked about how for each layer map, you get a bunch of hyperplanes in the domain, and then you pull these back all the way to Rn0. So that was not quite the full picture. Why not? So there's a couple things that can go wrong. Okay, so one thing that could go wrong is, what if all of your W's and your B are 0s? right? Then what this becomes is 0 equals 0. So your hyperplane is in fact the entire space. And so pulling it back will give you something that does not look like codimension 1. It will give you something of the wrong dimension. Or maybe they're all zeros. B is not 0. And then you have like number equals 1, which is empty. So there's nothing. Okay, so when I said hyperplanes, what I really should have said was affine solution set. The distinction being the dimension of the set. It could be that it has like the right dimension, which is 1 lower, or it could be something else. So that's something bad that kind of messes up this nice picture. Another kind of like bad thing is that this situation that I drew in the example, so this was our R2 to R3 example, it had 3 hyperplanes in 2-dimensional space, and they were arranged in the way you expect 3 hyperplanes to be arranged. So like this, where you have 3 hyperplanes, but they all actually intersect at one point, that's not something you would expect. Another thing that could be bad is you could have 2 of the hyperplanes be parallel and never intersect. So both of these things are kind of like messing up this nice picture that we want to build of like hyperplanes, you pull them back, you get things that are the right dimension, they intersect in ways that you understand. So we need to introduce some words, some conditions that, make this not happen. And so the first word is genericity. So definition, an affine solution set. So affine solution set here it's just the solutions to all these equations. So it's a bunch of sets. Each one of these equations gives you one set. So a bunch of these sets, an affine solution set in Rn is generic if all of this should have said affine solution sets, not hyperplanes, but intersect in the way with the dimension that you expect them to intersect. So like in this picture, if I pick any subset of my 3 hyperplanes, they intersect with like the appropriate dimension. 2 of them intersect in a point, 3 of them intersect in the empty set. So that's what this says. It says that an arrangement is generic if all hyperplanes intersect with the expected dimension. So for example, well, not example, that is, if I1 through IP are some of these sets, the intersection has dimension n minus p. So n is the dimension of the space, and p is how many of them you have. So each one knocks off one dimension. In particular, if you only have one of them, if you only have like SI1, it's saying that this has dimension n minus 1, meaning it's a hyperplane. So genericity implies hyperplanes, and it also implies that those hyperplanes like intersect in the way you expect them to. Oh yeah, great question. So if p is greater than n, you interpret that as meaning empty intersection. I should have written that on this slide. Yeah. Understand negative dimension to mean empty. Okay. Oh, there. Okay, there. It was a good point. I'm glad we talked about it. Okay. So we sort of want these layer maps to give us generic hyperplane arrangements, because when we want to prove things, that's the setup we want to be in. So we'll form a definition. We'll define one of these neural networks to be generic if for every single layer, the solution sets you get is a generic hyperplane arrangement. So it's just nothing bad happens at any layer. So is this a common thing? Yes. In fact, for a full measure set of parameter values, this is the case. Basically because having anything go wrong, you can express as an algebraic equation, and that algebraic equation has a solution set that has measure 0. Okay, great. So far we've defined polyhedral complexes. We've talked about how the layer maps give us arrangements of hyperplanes, and as long as we assume genericity, then they actually are hyperplanes and they intersect the way you think they should. And now we'll pull this all back together and we'll define complex polyhedral complexes associated to a neural network. So here's our neural network. So the point is, each layer map, like, I don't know, say F2, it gives you hyperplanes that live in its domain, Rn1, and those hyperplanes give you a polyhedral complex. It's just, you know, if here's R2 and you have like hyperplanes, this determines a polyhedral structure on that space. So for each one of these maps, it gives us a polyhedral complex on its domain. And I'm calling these M1, M2, M3, so on. So now what this is saying is that we can just pull everything back to the domain Rn0. So we do this inductively. So you start with the complex M1 on the domain. Then look at this complex here, or these hyperplanes, the ones that are form M2, and you take their preimages back in M1. So if this was my M1, maybe now I get, like, say, M2. I pull it back. And then I take this complex and I take its preimage all the way back here. And each time I just chop up the space using, like, yeah, all the possible ways to chop it up. And so that's what this is inductively defining. So you take the thing M1, you pull M2 back, and then you make that into a complex. And then inductively, you just like pull all the things back and you make a complex. Was that convincing? Okay. If not, feel free to, or if you think about it later and you're like, actually, wait, no, I don't believe you. You can let me know. We'll come back. Oh, that's the wrong direction. Okay. Right, so we keep pulling these things back, and each time we pull back one more layer, it subdivides the previous complex. So me and my collaborator Ellie Grigsby defined the canonical polyhedral complex to be the complex you get by pulling everything back and subdividing as much as possible. And it's more or less immediate that your function f is linear on each cell of this polyhedral complex. Just because the places where we divide the cells are exactly where the function is not linear. Okay. So, yeah, okay, so notice that this complex, which I'm denoting by C, and then the layer maps, it lives in the domain Rn0. Now we're going to do something slightly complicated. Just when you thought you had it. Yeah.
Is it vertical? Like, if you have a linear map in this canonical coherent, you get a sequence of functions?
So it is. So that's a great question. So I think one way to say that is, or one way to answer that is no. There are polyhedral complexes that I think do not come from any map of this sort. I have to think if that's true. Am I lying? I'm not sure if I'm lying. But one thing I can say is that there's definitely many different maps that give you the same polyhedral complex. So even if you can pick one, there might be other choices.
Okay, but if the polyhedron came from an actual,
yeah, neural network map, yeah.
You have a function that is linear on the cells.
Mhm.
That necessarily make the function, or doesn't necessarily you can make the function look like coming from a narrow network set.
It's a great question. So if you allow yourself to use any architecture you want, the answer is yes.
Okay.
However, if you only allow yourself to use like a certain architecture, then no. And like one way to see that is like for each architecture, there is some upper bound on the number of cells that you can get. People have written down what this is. I don't know what the number is, but so if you have more cells than that, then you couldn't do it with a given architecture. But I think you're getting a really good question, really important question, which is which architectures can give you which complexes? The answer is nobody knows. I'm kind of heading towards that. We know pieces of the story, but most of the story has not yet been established. Yeah.
My first thought in that directions, maybe that same behavior that, for example, linear system, linear simulation, not letting linear simulation has solution. For example, a question that I have is if of for either complex came from a never member.
Yep.
And another from another two.
That's a great question. Does the sum come from a? I guess you have to say which architecture, but yeah, you'd say like this polyhedral, this complex came from this architecture. This one came from that architecture. Does their sum come from some other architecture? Sounds like a great research question. Yeah, it's a good question. I'm not joking. Like that actually sounds like a great research question. Yeah. Any other questions before I keep going? Okay. Oh, I am going back. Okay, I'm working up to defining the next word, which is transversality. Okay, so we were talking about getting a polyhedral complex on the domain Rn0 by like pulling everything back. But something else you could do is you could just ignore the first part and just like consider this from like, this is Rnk-1 onwards. Consider that to be your neural network. And you could form the polyhedral complex here. So I'm going to call this F super K. It's like this, the tail end of my composition. So it's a map from Rnk-1 to R. So I could define the polyhedral complex F superscript K to be the polyhedral complex that you get from this. So it lives here. All right, so now I'm ready to talk about part 5, transversality. Okay, so transversality. So we're back to ways that this picture could fail. Before we're talking about genericity, now we're on number 2, transversality. So here is another way the hyperplanes, or bent hyperplanes, if you pull them all the way back, associated to a neural network can fail to look like what you think they should look like. Here's an example. So in this example, we're going to go from R2 to R2 to R1. The first map here is, I'm going to do the identity map followed by my ReLU, my nonlinearity. So I drew this as like the purple. The purple is the whole plane. You send it forwards by the identity map. And then what ReLU does is it just takes everything that's negative and makes it 0. So like, for example, a point where my red pointer is, it has negative x coordinate and positive y coordinate. So then the x would become 0 and the y would become, will just stay the same. So it would like be pushed onto the onto the axis. Similarly, points down here get pushed up onto that axis. and things down here, everything in the third quadrant here gets pushed onto the origin by the ReLU. Okay, fine. There's one layer map. Now let's do another layer map. This one is going to be just a linear map to R1. So it goes from R2 to R1. My map will be, for some m and n, mx plus ny. Oh, I guess I need a plus of b. I guess in this example, b is 0. And then I do my nonlinearity. So then the purple, okay, well, here's my hyperplane where mx plus ny equals 0. And on one side of this, I'll have positive numbers, on the other side, negative numbers. And then the ReLU will just make all the negative numbers 0. So like this purple will get sent to be like array, half of the line. Okay, so what's the problem? So the problem is when we take this bent hyperplane, sorry, this hyperplane here, and we try to pull it back, its preimage is the red set here. So this preimage is here. The problem is it's not the right dimension because everything in this third quadrant gets mapped to the origin, which is part of this hyperplane. So that's bad, right? Because we want to get hyperplanes. So the so-called bent hyperplane is in fact not a hyperplane. It is, in this case, a full dimensional part union a part that looks like a hyperplane. So the name bent hyperplane was kind of coined in the literature, I think maybe before people really understood that this could happen, that they're not actually hyperplanes. Always, I mean, they're usually hyperplanes, but okay. So what's the problem here? How do we frame this mathematically? So one way to frame it is using the concept of transversality. Okay, so I'm going to explain what transversality means and how it kind of is the problem in this example that we just saw. Okay. So first, I'm going to define or review, maybe, I don't know if you've seen transversality before, but the classical notion of transversality. So it is defined in like the smooth setting. That is, you have a map between, that should say manifolds, a map between smooth manifolds that's smooth. Not the situation we're in. We're working with piecewise linear things, which are definitely not smooth. So if you have this map and it sends a point X to a point Y. Oh, sorry, I haven't gotten to transversality yet. I'm still talking about the derivative. Okay, right. What is the derivative? The derivative, it takes the tangent space at your point X and it sends it to the tangent space at the point Y. And this is a linear map. So if you take the whole tangent space and you push it forward using the derivative, you get some linear subspace of that tangent space. All right. So in classical transversality, where everything's smooth, X is a smooth manifold, Y is a smooth manifold without boundary, and here Z is a subset of Y. This is going to be some submanifold of Y, like a smoothly embedded submanifold of Y without boundary. A lot of words. Okay, a smooth map F from X to Y is transverse to Z. When you write F, or I'm going to write F pitchfork Z for transversality. This is if you take the tangent space, or so you take any point P that is sent into Z, and you look at the whole tangent space at that point, and then you push it forward by the derivative. And then there's also the tangent space at Z. If you add these things together and you get the full tangent space at at y, this is called transverse. Let me draw a picture. Here's a picture. So in this example, my x is going to be r, my y is going to be the plane, and z is going to be this curve. So it's a one-dimensional submanifold. Okay, so I pick a point that's in z. Okay, and I say P is something that gets sent to Z. And I take my all of my X and I map it forward, and that's this curve. So you see that this curve crosses Z. So the tangent space here gets pushed forward, and it becomes like the little tangent space here. But then that plus this gives you the full two-dimensional tangent space. Whereas like this situation, where you don't cross Z, this is not transverse, because the tangent space here to the push forward tangent space is parallel to the tangent space for Z. So you don't get the full two-dimensional tangent space. Questions? Yeah. A really great reference for transversality is a book by Gilliman, or I don't know if I'm saying it right, but okay. So what's the point of transversality? Essentially, it's this theorem. This is the classical theorem. That if F is transverse to Z, that when you pull back Z, you get something that has the expected dimension. And the way to say expected dimension is that the codimension of the preimage in your domain is equal to the codimension of Z and Y. Okay, so just to go back before we get too abstract, right? The problem here was that we pulled back this one-dimensional thing, a codimension one thing, and we got something of the wrong dimension. So that's kind of the situation that transversality says does not happen. But this is classical stuff in like the smooth setting, and we're in the piecewise linear setting. So we need to just like adapt this a teensy little bit. So we need to adapt transversality to the piecewise linear setting. So what could you possibly do? Well, basically, the only thing you could do is you look at each cell of your polyhedral complex and you ask, is the map from that cell transverse? Yeah. So actually, what I just said is essentially this definition. Let me read it. Yeah. So let X be a polyhedral complex in Rn, and Z a smoothly embedded submanifold of Rd. And then you have, if you have a map F that goes from the domain of X to Rd that's smooth, actually just continuous, sorry, that should say continuous, not smooth. You can define F to be transverse on cells if, and we're going to write this as F pitchfork with a C to denote the cell, if when you restrict F to the interior of each cell, that map is transverse. So it's like the whole thing can't be transverse because it's not smooth. But if you just look at what F does on a single cell, it's linear, so it's smooth. So you can ask, is that map transverse? And so you just look at each cell and you say, is it transverse on every single cell? Yeah. It's local in the sense that it's cellular. Yeah. Okay. It's kind of technical. I apologize. So, right. Okay. So the point is, what I'm leading up to is, I should say, by the way, that I and my collaborator had defined a notion of transversality. And then Marissa Masden defined a better notion of transversality. So I'm going to give her notion here. It's super transversal. So here's the definition. So you've got your neural network, and you've got all these complexes. The M's are the ones that come from the hyperplanes. And then the C's, these are these complexes you get, but you go from here forwards and you like pull everything back to here. So you have in each of these you've got a C. Okay. So the definition is that the map is super transversal if, when you look at one of these layer maps, here the purple Fi-1, so from here to here, if that is transverse on cells of this guy to the interior of each cell of this guy. Okay, like, whoa, so many complexes going on. It's like, who can keep track of this? Yeah, it's really hard. Basically, at the moment, I would say, like, don't worry about it too much, but just the point is, like, everything possible is transverse to everything else. It's like everything you see anywhere is transverse. And then after a while, you can go back and, like, try to internalize this. It takes a while. It's like, basically, instead of pulling everything all the way back, you can, like, pull things part way back, and you can ask, are these intermediate? Anyway, yeah, everything's, like, as transverse as possible. Okay, so that's kind of the long lead up to the question, what, quote unquote, went wrong in our example? So this was our example. I just copied it. So we had R2 to R2. You do the plane, the identity map. It gets sent just the positive orthant, and then you have this hyperplane, and you try to pull it back. So if you figure out what all of the relevant complexes are, and I tried to illustrate this. Well, I tried to illustrate something. Maybe you can just kind of believe me, but here's a complex that's the M1 complex here. The complex C of F2 lives here, and it looks like this. And so the point is that when you map this complex forward to this complex, you get that this map is not transverse on cells of this complex to the interiors of cells here. Okay, this is very pretty technical. Basically, what it's just saying is that, yeah, transversality fails in some way. And so when we try to pull these hyperplanes back, we get sets of the wrong dimension. And there's this very technical condition saying that that can't happen. Maybe don't worry about the details too much right now. I guess the takeaway is that there is a concept called transversality, and it describes this phenomenon of preimages having the wrong dimension. And you can make a version of it for neural networks. Okay. So you might ask, is this thing likely to happen? And Masden proved that the answer is yes. For a full measure set of parameters, the map is super transversal. So those bad things that we were worried about, this is telling us that they only happen on a measure 0 set. So here's a theorem that if your map is generic and super transversal, so remember, generic was like that hyperplanes intersect the way you expect them to. Super transversal was this idea that when you pull things back, the dimension doesn't get messed up. If that's true, then the bent hyperplane arrangement has the appropriate dimension. That is, it's the dimension of the domain minus 1, and it's the skeleton of this canonical polyhedral complex. So what have we done? Essentially, we've just said the picture that I drew for you first, it was a little bit of a lie, but it was only a lie on a measure 0 set. Like this picture, like this is the bent hyperplane. So I was like, oh, so nice. And what that theorem says is that this is the generic picture. It happens with a full measure probability. Great. Okay. So what have we done? We've said that for all but a measure zero set of parameters, we have this nice polyhedral complex that we can work with, and it's n-1 skeleton is the pre-image of these hyperplanes that came from the layer maps. Okay, let me pause and ask if anyone has questions. There are a lot of technical pieces, so I'm happy to go back over any part of them. Did I lose you? Yeah. Yeah, I'm talking about with respect to Lebesgue measure on Rn. Yep, good question. Yeah. So, right. So, well, I guess it depends what you want to use this to prove. I think something you're probably kind of thinking about is how, as I change my parameter, how does this complex change? Right. And so, yeah. So these measure zero set of bad parameters is where the complex changes, basically. And so if you're trying to prove something like a local result, then it doesn't really matter if you're near one of these bad ones or not. But if you want to prove something about all of parameter space, then you have to start to worry. I don't know. Is that getting at what you were thinking about?
There's something strange happening in the training of the model when the parameter is here. I'm not sure.
Yeah. So okay, let me reinterpret your question. Just I think what you're asking is if we watch as we train our neural network, at each parameter we have this polyhedral complex, and we're training, and then we get a different polyhedral complex, we're training, and we get a different polyhedral complex. You're asking, well, lots of things. One is how do these complexes change? Can we kind of understand that? What kind of complexes are we more likely to maybe to go towards? Yeah, I guess I could continue expanding on that, but I think all of these are kind of in there. Yeah. Other questions? Yeah.
For example, application of linear features dynamic systems.
Applications of this to the dynamics of gradient descent.
No. Present is this linear application, but there to go to n and I plus 1 to R and I 2.
Oh, can you think of this as a dynamical system? I was actually just talking with someone about this earlier today. Yeah, I mean, I guess that's a great question. So can we think of this as a dynamical system? I think the obstacle to thinking of it as a dynamical system is the fact that all of these dimensions could be different. Yeah. Yeah, you definitely could do that. So I guess your question was, are there people doing that? I mean, I think the field is just huge. So I'm sure there's probably someone. Part of the challenge is keeping up with the literature, because there's just lots of people doing this from different directions. I'm not quite sure what the state of the art is in terms of viewing this as a dynamical system, but yeah, that's good. Okay, so I wanted to tell you another theorem. So this one's also due to Marsden. So it says that if you have a neural network that satisfies these two things, generic and transversal, then nothing bad happens. So we actually have like a polyhedral complex in our domain that looks like what we think it should look like. When you start assigning these sign sequences, remember the sign sequences like pluses and minuses and zeros, that this assignment is injective on cells. So if I have two different cells and I record all the signs of all the different neurons, they will be different somewhere. In general, that is not true. If you don't have generic and super transversal, you can get a complex where there are two different cells. It's okay. Two different cells that have the same sign sequence. So that's weird. But moreover, you can read off the dimension of the cells from the number of zeros in the sign sequence. So remember the zeros, right? So like we had pluses and minuses, like which side of the hyperplane you're on, and then the zeros were like if you're on the hyperplane. So in this setup, like basically because when you pull things back, the dimension stays what you think it should be, the number of zeros is exactly the number of dimensions that you lose. So you can read off the dimension of the cells from these sign sequences. Okay. So I think what this is telling us is that these sign sequences are like really powerful in this setup. They encode a lot of information. And in fact, I think, I mean, I didn't write this, but I think a great question is what possible sign sequences can you get? I think this is a hard question. So, what is the collection of sign sequences for all the different cells, for all the different cells? So like each cell has some collection of, you know, pluses and minuses and zeros, like, you know, plus, plus, I don't know, minus, plus, minus. Maybe this one has like a plus zero, you know, I don't know, whatever. There's, each one's got, and so how can you describe these sets of sequences? Like, are there some sets that you can't have? Are there obstructions? Are there guarantees? Like, are there local things? Like, I don't know, it's like, this is an open question, so I'll just say obstructions. Or on the other hand, are there constructions? Like, can you show that there's some way to get a certain sign pattern? Right now, the field's pretty much wide open. Oh, maybe that's my last slide. That's my last slide. Okay. Okay, I think I must have talked quickly. So let me just like, since I do have a few extra minutes, let me like kind of back up and just like review. So in my first lecture this morning, I introduced this class of functions. And I've kind of started introducing these questions like, which architectures can do what? You know, how can we understand what functions like do, blah, blah, blah. So in this lecture, the point was that for this type of neural network, there are these polyhedral complexes. And like, they're kind of they're nice. They're like a nice mathematical structure. And it's a topological structure. And they come with sign sequences. And so it's like the math, like you want something that you can like grab onto to try to like prove theorems. And so I think these these canonical polyhedral complexes are like a thing that you can use to start to try to like prove, prove theorems that start to answer some of these questions. And so the point of all of this was that as long as you rule out a measure zero set of like weird parameters, that these complexes kind of have the structure that you expect them to have. Okay. So that's the end of this one. Questions? I still have 26 minutes left, so I can go on to my talk 3 after this, unless you guys are tired. But, what do you think? Should I go on to talk 3? Yeah? Okay, all right, let's do talk 3. Do you mind? Yeah. Did I send it to you? Yes, you're quite like what do we expect these complexes to be? It's a great question. Not known. All right, why don't we like pause for like 3 minutes, because I didn't send Jose Luis my slide 3, so I'm going to do that, and we'll start again in like 3 minutes. Is that okay? Sorry about that. Okay, so I think I must have gone way too fast because I thought that was going to take longer than it did. So that means I probably went faster than I should have, and maybe you guys have questions. So before I keep going, let me pause, and that's like, does anybody have questions? Do you want me to go back and like review any parts of this? Okay. I'll just say again, I'm going to put all of my notes online so that you'll be able to access them. So if you were frantically trying to take notes and you missed something, don't worry about it. I'll give you these. Yeah. So I think it's always just a number. Like there's I mean, so I'm talking about this like one particular family of neural networks, the ReLU, feed4, blah, 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 blah. In that setup, they're definitely numbers, but there's so many different variations that like maybe there's some weird version where it's a function. I don't know. Does anybody know? Has anybody heard of? Okay, I think I'll say 99.99999% of the time they're just numbers. Yeah. In this decade, like, what do I think we're going to accomplish? Oh, that's an that's easy question. I really have no idea how to answer that, but I think I can say that I think like momentum is like picking up. Like I think more and more people are starting to do this, and so I feel like whatever I said, like the rate of progress is going to be like this. So whatever I can say now, like 3 years from now, will be like just really different. I don't know. Maybe other people have more insight than I do. But, all right, so this brings me, because I speak apparently too fast, to sort of the third part of what I wanted to talk about, which I'm calling topological expressivity. So I've got 19 minutes left here, so I'll start to talk about this, and then we'll, continue tomorrow. Okay. So, so we'll start with a motivating question. So there's many different motivating questions that you could ask, but here's the one that I chose to ask. Which architecture should you choose? So imagine you're someone who actually wants to like use these things in practice. So you have a data set and you want to find one of these functions. So to do that, you need to pick which architecture of functions meaning which class of functions you're gonna look at. How do you do that? Which one do you pick? Right? Like, so this is like actually an important question, in part because training is very computationally expensive. So like if you can avoid training, like basically like the smarter you can be about how to start doing this, like the more you're gonna like save yourself like time and money and destroying the planet and all that stuff. So you somehow you want the architecture to be complex enough to capture, you know, whatever phenomenon it is that you're trying to model. I remember like our discussion of overfitting versus underfitting, but right, not too complex. So currently, there really is not yet a good full theoretical understanding of how to pick an architecture. In fact, there's an entire field of study called neural architecture search, which has to do with trying to figure out which architectures often work better. So hopefully, as mathematicians, topologists, geometers, and so on, we can contribute to this. So let me just try to refine this question a little bit. So some of these we've already kind of seen. Question 1, which functions can be realized by which architectures? We don't have a full characterization of like no way to characterize the collection of functions that you can get from a specific architecture. There are bounds, like you can say like, you know, for this architecture, you can get functions where the polyhedral complex has at most 100 pieces or something, but that's not like an if and only if statement. So I mentioned this. Are there topological obstructions or guarantees? And kind of related to that is like, are there useful notions of complexity that have to do with topology or geometry? And another one is like, how do these layer maps act topologically, right? So as you're like doing each layer map, you're like changing your set, and like how are you changing the topology of your set as you push it through the different layer maps? There's probably many, many more items we could add to this list. I just listed a few. Okay. So section 2, architecture-induced constraints on the topology of sublevel sets. Okay, so first we're going to recall what a sublevel set is. So suppose you've got a function, f, that goes from Rn to R, and you pick a threshold, t, in R. The sublevel set is just all the points where the function takes on the value t or below. So it's the preimage of the ray, negative infinity to t. The level set is where points where it actually equals t, and then the super level set where it's greater than t. You guys have been thinking about like Morse theory, so I guess this is probably like, yeah, I got it. So we can call these decision regions. If you think of your function as answering some yes/no question, you know, is this a picture of a cat or not? You can think of an output above t as meaning yes, an output below t as meaning no, output of t being on the boundary. So you can this is useful for like yes/no binary classification questions. Okay, and we've got these complexes, right? So if you have a polyhedral complex in Rn, and you are mapping to R in a way that's like linear on cells, meaning cellular, then you have these polyhedral complexes. So the complex consisting of the places where the function is lower than t, where it's equal to t, and greater than or equal to t. So question, how does the architecture, which remember is the list of n0, n1, etc., how does that impact, constrain the topology of these sets? So one topological attribute you can ask about is boundedness, right? That's topological, or maybe it's more geometrical, but it's something. So this is an example of a theorem that I think is pointing in a really cool direction. Let me tell you about it. So it's been discovered independently at least 3 times because it's hard to keep up with the literature. So here's what it says. If you have one of these ReLU networks, F, and then like, right, it's got its structure. So if the width of F is at most n0, so n0 is the size of your domain, and so we're saying that all of these intermediate intermediate spaces are no bigger than Rn0. So it's like very kind of narrow, but maybe deep. In that setting, each of the 3 different decision regions is either empty or unbounded. Right, so this is like, you think it's like the no region, the borderline, and then the yes region. So I think this is a really cool result because it's starting to get at this idea that the topology of sublevel sets is somehow influenced by the architecture. I don't think this particular theorem is that useful in terms of applications because people don't actually work in practice with networks of this form, ones where all the intermediate spaces are kind of small. But I think it's like a first step in what I think is a cool direction. So what I'm going to do in the remaining time is I'm going to try to talk a little bit about why this is true, why this theorem is true. Before I do that, any questions about like the statement of the theorem, what it's saying or why we care? Okay, so great. Well, let me try to like convince you roughly why this might be true. I'm not going to prove it, but it's like just kind of say some words that kind of hint at why it's true. In a particularly simplified case, the simplified case is that all these intermediate spaces have the same dimension. They're all the same. And also, all of the affine maps have full rank. Okay. So consider the image of the domain. So that's our original domain in the final hidden layer. So that's RD. So you take it here and you just map it forward until you get here. There's one more final layer here. That final layer does not have the ReLU, the nonlinearity on it. So you get to here. Oh yeah, so here's a picture. So here's my first copy of Rn. I've got like all of Rn, and I like push it forward all the way through until you get here, and like maybe now it looks like this green set. So the claim, and I'm going to call this set S. So S is the image of the domain under like all the maps up until this point. So a claim is that if S has a boundary, it might not, but if it does, and if there's a point in it, if you look at a point in it, if you take like, say that point, if you look at where that point came from in the domain, it's unbounded. That's the claim, that points in the boundary have unbounded preimages. So just believe that claim for right now. Let me tell you why it matters. So now consider this like the final layer. I guess I'm calling it G here. So it goes from Rn, where your S lives, to R. And there's the hyperplane H that is the preimage of T. So this red hyperplane, that's what gets sent to T for any particular value of T. So there's 3 possibilities of what H could do. It could be that H misses S entirely. So in that case, the preimage of the intersection is empty. Okay. The second case is that H does hit S, like in this picture, but it does not hit the boundary of S. So this is the topological boundary of S. That intersection is empty. So what's that saying? Well, H is a hyperplane. If it never hits, it hits the set, but it never hits the boundary of the set. Okay, that means that it's unbounded, right? And so then if you just pull that whole unbounded thing back, you get something unbounded. And then the third possibility is that H does intersect the boundary. If it does intersect the boundary, then if you believe this claim, the preimage has to contain an unbounded piece. So like, if you believe this claim, regardless of what happens, either the preimage of this hyperplane is empty or it's unbounded. So that was about a particular threshold, but we're looking at sub-level sets. Okay, so all the points where the function is at most t. Well, that includes all the points where the function equals t. And since this is true for every single t, it's true for the whole set. So the preimage is either empty or unbounded. Okay, so this is me attempting to wave my hands at proving this claim. So the claim is that in this setting, all the ends are the same, all the maps have full rank, that every point in the boundary has unbounded preimage. So here's sort of like a hand-wavy proof of that. And note that this claim is going to really use those assumptions. Okay, so let's just like think, what does the very first layer do? So your first copy of Rn to your second copy of Rn. So here's Rn, and I drew some hyperplanes, and like you push it forward, it becomes this, and then you do the ReLU. The ReLU makes all the negative things 0, and so you end up with this picture. Okay. So if I pick a point in the boundary here, it came from an unbounded piece. Okay, so that was the first layer map. Now let's consider the next layer map. So here's this, I've just redrawn it here. So you map it forward, maybe now it looks like this. And then you apply the ReLU, which takes all the negative stuff and makes it 0. So now it looks like this. Now again, if you pick a point in the boundary, what could have happened? Like, the boundary is where stuff got collapsed. And so what could have gotten collapsed onto it? Either it came from a point in the boundary of like the previous layer, or it was a whole unbounded piece that got collapsed. And so sort of inductively, you keep going, and in the end, you see that like every point in the boundary has an unbounded preimage. This is not rigorous, obviously. I direct you to one of those papers that prove this for a rigorous proof of it. Yeah, so this just says keep doing induction, and you get the claim. Okay. This hand-wavy proof was in the setting that all the intermediate spaces were dimension n. But like, what's the problem? Like, you might be wondering, like, well, why did it matter that they were all the same size, all the same ends? Like, what would go wrong if one of those intermediate spaces was bigger? So here's an example. Like R1 to R2. Obviously, 2 is bigger than 1. Right? Okay, so here's R1, and you send it into R2, and then you do the ReLU. And so the ReLU makes all the negative stuff 0, and so we get this green thing. Okay, what's different now is that every single point is a boundary point, right? Because it's a lower dimensional thing. Not just the points where like something got collapsed. So that's like why the Rn mattered. Yeah. Okay. To do this formally takes a lot more work. Yeah.
When you mentioned the theorem, you say that Nobody comes to the thing. What?
That's a great question. Yeah, so back to the question of which architecture should you pick? So when you're doing training, basically if you have a really deep network, like very many layers, it's hard to train the network. Like in theory, a really deep network could do a lot of things, but when you actually try to do gradient descent, like it just doesn't converge very well often. It's like vanishing gradients, and so there's sort of like this trade-off, which I actually don't know too much about. There's probably people here who do, but about like depth gives you more flexibility, but it's like harder to train. And so like this is theoretically like a super flexible network structure, but in practice, like I guess it's just not very useful. Okay. So I'm now reaching the end of my sort of time for today, but just to kind of like wrap it up, let me just say, so what have we done? So we're starting to argue about how the structure of the network impacts the topology of the sublevel sets. And so like the game, or like the goal that we could hope, is that like we could really nicely describe like what the topology could be based on the architecture. And like we're starting to get results in that direction, but like much more is possible. And I'll say more about that next time, but this is kind of just like the inspiration. Yeah. Yep.
Meaning that, for example, when I extend each of universe symmetrical L, the interval is close to minus simply.
Oh, no, that's because I wasn't paying attention. That's a typo. Yeah. Okay. So next time, tomorrow, I'll continue talking about this, different aspects of topology and topological expressiveness. And then at this rate, I'm going to have to plan lecture 5. All right. So we'll stop there. Thanks.